this lecture is essentially independent from what I spoke about last week, so you certainly don't need to remember if you weren't here. You don't need to think about what I spoke about last week. There will be a little, well, there will be a connection which I will outline, but it's not essential for what's going to happen. And to sort of motivate what I'm about to talk, I put up this recipe that at least some physicists use to solve the KPZ equation. I'm not going to argue why KPZ equation is important and all that. It's the title of the program that's being run here, so that's probably enough. And so this is the KPZ equation with some choice of constants, right? It's in 1 + 1 dimension, and this is the space-time white noise. So what if I want to solve it? So that's supposed to be a model of growth of a random interface. And so the first thing one does is one needs to understand what that equation means. I mean, singular, and one needs to explain what the solution means. And one point of view is easy. Let's just do a change of variables. Think of u as being the log of something. And then this equation turns into what's called the stochastic heat equation. And that is completely well posed. It's not hard to show. So we are solving this stochastic heat equation. Now, to solve that, it's useful to look at its moments. So the solution depends on t and x. So what I'm doing here, I'm looking at moments, which is the average of the product of the values of z at the same time and different space locations. So this is a function in time and n space locations. And it's not hard to show, essentially, using the definition, using this equation, that this function satisfies an autonomous evolution equation, which is known as the quantum delta Bose gas evolution, which is the following. The time derivative of this expression of the joint moment is a spatial operator applied to the same function, and the spatial operator is the Laplacian plus the interaction that's completely concentrated on the diagonals. And that's just the sum of the delta functions of the pairwise differences. OK, so why is this good? Well, this equation happens to be solvable by the techniques of the Bethe ansatz. Namely, one can diagonalize the right-hand side. One can diagonalize the spatial operator in the right-hand side, which goes back to the pioneering paper of Lieb and Lineker. In the repulsive case, that's when there is a minus here, and then Maguire and Young did this further to bring the theory to more suitable form. OK, so that would give, if we use that, and that would give us these moments. And so from those moments, to get back to the distribution of the solution of the KPZ, I'll need to solve the moment problem. I need to recover the distribution from the moments. And there is a slight problem there. That problem just does not have a unique solution. And one can still get around that using what physicists would call replica trick by analytically continue the z to a power essentially to any power, not just integral powers, and then extracting some information from there. And I'm not going to discuss how well defined that is, but that's the recipe that has been successful. Okay? And there are papers where people got the results one expects from universality using this scheme of approaching the KPZ. OK, so here is a possible regularization of this argument that does not involve replica trick and in general is mathematically sound. So first of all, I'm not going to start with KPZ. I'm going to start with a certain discrete system, discrete in space, continuous in time, which is approximated by KPZ in a certain large time limit. OK, so then mimicking what I had on the previous slide, the first thing I need to do, I need to find a replacement for the moments. So the moments in the previous slide played a big role because they satisfied a system of equations one could solve. So I need to find a substitute for those moments. Now, once that is done, hopefully those moments satisfy an autonomous system of equations. And I want to solve that system of equations, hopefully by some version of Bethe ansatz, by diagonalizing the spatial operator, but maybe by some other tools. In any case, if I solve it, I'm in good shape. So if I solve it, then I want to go back to reconstructing the distribution for the solution of my discrete system and then take a limit to kpz. So once I take that limit, the argument is mathematically rigorous because typically proving the weak convergence of solutions for the discrete system to kpz is not such a big deal. It still requires efforts, but at least it's doable, and it's doable in a sound manner. Okay, so this is the scheme that I will try to explain in action for one system, which will involve a parameter q. We typically refer to it as q-TASEP. It's also realizable for ASEP, and I'll mention this briefly. Now, more exactly, what's realizable is the first three steps. The fourth step, which is to take what one gets from a solution and then take the limit to kpz in any kind of an explicit fashion, at this moment can be done for certain specific initial conditions. We hope it can be done more generally, but what's done now is that there are some initial conditions for which the whole scheme is realizable, and I'll mention what those initial conditions are. But again, I'm convinced that this can be pushed to the same level of generality as this scheme physicists believe exists in the replica world. Okay, so
and the advantage of it will be that you don't have problems with that you can go from moments to distribution.
Yes, yes, and then there is no. So in the early works, well, early, okay, 4 years ago, in the earliest papers of physicists realizing this scheme, they in fact reconstructed the wrong solution using the moments. Okay, and so in this replica thing, okay, if one does it right, it gives the correct thing. But if the only information you have is the moments, you don't, I don't know, I wouldn't quite be sure how to do the replica. Of course, the universality should guide you, but again, the first physicist papers were claiming that, oh, the universality is broken, we get the wrong answer, and so on. Then it got corrected. Okay, so it just gives you something to be sure of, and to me, this is good. Okay, so what's the Q system? So the Q system, as I said, this is q-TASEP. It's a system of particles on a one-dimensional lattice. The particles jump to the right independently with exponential weighting times. They have different rates, and the rates depend on the distance to the particle in front in the following way. They equal 1 minus q to the power, which is the number of empty spaces in front of the particle. 1 minus q to the gap. The fact that this converges to kpz is not obvious, but is correct, and so I'll just assume it and proceed, and then explain a little bit later how that happens on the level of formulas. Okay, so this formula was on my slides last time. This is the formula for the expectation of moments. Okay, so that formula already swallowed 2 steps in it. I found the moments. I didn't say they satisfy an equation, but I knew what moments to look at, and I get the final formula for what they actually are at any time. Okay, so the moments are the q moments of the positions of these particles. I need to fix a few n's, which are the numbers of the particles. The particles, I'll take the initial condition where everything, all particles sit on the left and there is nothing on the right. And so then I have the first particle, second particle, and so on. So I pick a few, number n1, n2, and so on, ordered. And then I take the q moments of their position. So q to the xn1, blah, blah. There is an n1 here, but it can be moved to the right-hand side. It's irrelevant. And so then the expectation is given by this formula. I'll come back to this formula later. It has the interaction term. So the number of integrations is the same as the number of particles here. This is the interaction term that involves Vandermonde and q skewed Vandermonde. And then this is the term that's just the product of something elementary over all variables. The contours are a little weird. So there are high order poles here at the point 1. And so the innermost contour goes around 1. And then the next contour goes also around 1, but also around q times the first contour, so that to avoid the poles coming from here. And the third contour goes around these 2 multiplied by q, and so on. So they need to expand. So I'll call them nested contours in this situation. So the proof that I presented last time involved McDonald processes and the techniques the techniques related to the operators diagonalizable by those. It seems to be an overkill. It involves too much structure to prove a reasonably simple statement for an explicit system. So I want to say how to do it simpler without any McDonald formulas. Here's what it is. So the statement below here says that this moment, viewed as a function of time and space are these numbers n, the number of particles that were being picked. It satisfies a certain autonomous system of equations. And that system has the form the time derivative is equal to a spatial operator applied to that object. Now, to describe what that spatial operator is, it's easier to me to, instead of just writing it out explicit, well, which I do, but it's easier to understand it in the probabilistic language as well. So this operator here is actually a generator of a different Markov chain. So let me explain what that Markov chain is. The Markov chain is the following. One looks at particles, so this is the so-called zero range process, so one example of it. One looks at particles, again, living in a lattice, but then at each side there may be several particles. So there's no exclusion constraint. And then the particles evolve in continuous time, where each particle is going to jump to the left with the rate that's equal to 1 minus q raised to the power the number of particles at that location. Okay. So this specific zero range process I will call the q-Boson stochastic particle system, and it will be clear in a second why I'm using that name. And it's not hard to check from the definition of q-TASEP, from the evolution of the q-TASEP, that if one forms these moments, then they are going to behave according to this equation where h is the generator for this Markov system. So this is the explicit form of the generator. I need to sum overall locations, 1 minus q times ci. So ci is the size of the cluster sitting at that location, times the difference of the values of that function at the location where the particle jump and at the location at the initial one. Okay, so this is the replacement for the delta Bose gas. This is what the moments satisfy. Okay, it's already somewhat of a miracle that they satisfy anything, because what happened is that we took a system with infinitely many particles, and we extracted from it something that essentially involves one particle, if I just take here k equals 1, or two particles, or so on. So this allows me to reduce questions about the dynamics of infinitely particle system to the dynamics of a one particle, two particle, three particle system. It won't give the whole information, but it will give something. Okay? So this idea is present actually in the probability world and has been present for a number of years. It's known under the name of duality of two Markov chains. And let me just phrase what it is. If you have two Markov chains that are coupled in the sense that there is a function on the product of two state spaces, this state space and this state space. And what you can do with that function is that you can either evolve this chain in time and keep this initial condition fixed, or you can evolve this chain in time and keep this initial condition fixed. The end result on the function that you have will be the same. Okay? So what happens here is that the two systems that I had, the q-TASEP and this system, they are dual with respect to this particular function that's a function on the product of two spaces. It's not an intuitively obvious concept, and you don't need to internalize at the moment. It's much easier for me, at least, to think that you just have some special observables that satisfy an autonomous evolution equation. Okay? Okay, so if I solve this system, which I am about to do, I will have the information about the q moments of q-TASEP, and then solving the moment problem there, which is doable uniquely, sometimes explicitly, in general not so explicitly, will give me the information of q-TASEP, and ideally that can be taken to the KPZ limit.
So this zero range is has invariant measures. This one is trivial invariant measures.
What's the invariant measure?
No, this zero range dynamics. Do you have invariant measures?
Yes, and I will say that in a second. Yes, You had a question too.
Yeah, just the initial condition that you have an expectation, and I
Yeah.
don't remember what with the initial condition f0 and down one line below.
Yeah.
Is there
So
what is being averaged over at time 0? That's before anything.
well, it's if your initial condition is actually random. My initial
So there might
condition.
be some.
It may be in.
Was not.
I gave the fixed initial condition can be any initial condition under the assumption that I have finitely many particles to the right from any location. So, so that I can number the particles, first, second, and so on. But I can take any random initial condition. It doesn't matter. This statement stays in place. It's not based. Thank you for the question. This statement is not based on a concrete initial condition. It works for any initial condition. All right, now I'm going to do something to this generator so that it would look simpler. It doesn't look so appealing at first, but it's actually not that bad. What happens is that, similarly to the delta Bose gas, is that if these particles here are all away from each other, right? So there are no clusters. Then the evolution is just the free evolution. Each particle jumps with rate 1. Nothing else happens. So this is my generator. That's when I'm away from the walls of the Weil chamber. That's when the particles are not sitting on top of each other. Now, when particles start sitting on top of each other, it gets harder. But one way to encode it, it turns out, and that signifies the integrability, is that I can encode it by the following two particle boundary conditions. So let me spell it out. If I'm sitting on the border where two particles are at the same location, if I try to move, I will assume that these ends are ordered. So these are the locations of the particles. I can order them. So if those particles try to go in the wrong part of the space, so they are ordered, but the particle that's not supposed to overcome the previous one tries to do that. What I need to be able to is to relate the value in the wrong part of the space to the value in the right part of the space. And that's being done here. So see if that operator just means that one of the ends gets lower. And so if I have two ends that are being equal, when one gets lower, that is related to the situation when the other gets lower. And so by using that relation, I can keep my particles ordered. So that's the reduction of the evolution equation to the free evolution equation in the Weil chamber where everything is ordered, plus the boundary conditions on the border. And the essential part is that those boundary conditions only involve two particle conditions in here. In general, there will be 3, 4, and higher order things for a general system. You can sort of always play that game, but the number of boundary conditions will be larger, and the feature of the integrability is that two body interactions is enough for that. Okay, now that's not hard to check. I'll be happy to show how this produces this thing very quickly. It's just a geometric series summation, essentially. All right, so then it's enough for me. What I said is enough to check this formula for the q moments. Namely, I need to take the right-hand side and verify that when ends are far from each other, they satisfy the free equation. And when they're close, they satisfy this boundary condition. And if you just look at the formula, what will happen is that this part here, see, this part is n independent. Okay? This part here, it just satisfies in each variable the free evolution equation. Just a function in one variable, you check it immediately. And this thing here is responsible for the boundary condition. What will happen is that if you apply this simple operator to this part, it will spit out one denominator here. So it will spit out something like z1 minus qz2. That's going to cancel the denominator here. The end result will become skew-symmetric in z1 and z2, and thus it is 0. So it's basically the verification in one's head. Once the formula is written, this is really the solution to the evolution equation. It takes a little bit of time to check that the initial condition works, that this is actually OK for the step initial condition. And I'll get to that a little later.
And you can write a similar but maybe more complicated formula for non-step initial conditions?
So that will be the subject of the rest. That's essentially what I'm trying to do. Yeah. Okay. Yeah. If you've seen Bethe ansatz, then this type of a reduction is always done in the approach. It's called coordinate Bethe ansatz. This is the Bethe ansatz that Bethe himself invented in 1931. There is a more advanced technique called algebraic Bethe ansatz developed by Fadeev's school in St. Petersburg, and I'll just mention that this system is also integrable in that sense, and so I'll just mention it and not do anything about it. If you haven't seen this type of integrability, just skip this slide. So what I wanted to say is that if I put the periodic boundary condition rather than being on the whole lattice, then this quantum Hamiltonian, where B's and B daggers satisfy Q commutation relations, these form a Q deformation of SL2. They're also called q-Boson algebra. Then this Hamiltonian turns into the generator of my q-Boson particle system under a particular interpretation of the B and B dagger operations, which are written here. So there are certain difference operators that one can do. So this the important thing is that this Hamiltonian comes from the standard algebraic Bethe ansatz procedure, which involves an R matrix and the monodromy associated to it, and then the extraction from the monodromy matrix, the Hamiltonian. So that was actually the first time that this system was introduced by Sassamoto and Vadati, who observed that, but didn't do essentially any analysis after that. And that's the reason that the system is named the q-Boson system. Okay, so again, a remark is that the ASEP, the asymmetric simple exclusion process, which is the system of particles, again, on the one-dimensional lattice where the particles jump left and right with different rates, also has a similar story that I'm not going to talk about. I'll just mention what it is. So the moments here are different. These q's are observables of a system that measure the number of particles to the right from a particular location, and then, well, taking the discrete derivative of that. And so these are my generalized moments. And the expectation for that has a similar formula. There is, again, this cross term, and there is a one particle term. Again, there is a duality story. It turns out that ASEP is self-dual. There is a duality of many particle ASEP, infinite particle ASEP, and finite particle ASEP using this type of functional. And that was actually noted by Schutz. And then Tracy Whittem worked on ASEP using Bethe ansatz, which is related to what I'm about to talk about. But again, I'll leave that aside. I'll just mention that a similar statements to whatever I'm going to say exist for ASEP. Okay, so I'm trying to, back to my original story, I'm trying to diagonalize an operator. Now this operator here. So this is an operator in the space of functions on configurations like that. And that operator is not self-adjoint. I'm working in an infinite dimensional space with an operator that is not self-adjoint. My background in function analysis tells me this is not doable. There is no spectral theory for non-self-adjoint operators. Okay, I mean, at least I haven't seen It's not self-adjoint with respect to the invariant measure. It's not self-adjoint in any L2 space that I can come up with. What replaces self-adjoint, ASEP actually is, so that makes it a little different, but this one is not. What essentially replaces it is the following statement, that if I go into the L2 space with respect to the invariant measure, which is written here, then the operator is not self-adjoint, but it's self-adjoint with a twist, where this twist is the parity transformation. This is the space inversion. This is x to minus x in this space. So this fact that my operator is invariant with respect to such a thing is actually known under the name of PT invariance. And it's been shown in some situations to replace self-adjointness. Not for spectral analysis, though. At least I haven't seen those references. So that somehow replaces self-adjointness. Okay? But still, the operator is not self-adjoint, and what I mean by the spectral analysis is not clear. So I will try to show what I mean.
So, yeah, so you're going to say in what sense it replaces self-adjointness?
No. I can say it in one phrase now, is that in the proof where you would like to use self-adjointness, you manage to get away with using this property instead. Okay? That's the best thing I can suggest, really.
Real spectrum?
No. So I don't even know what to call spectrum, and you will see in a second. Okay?
Can you say what you meant by ASEP being self-adjoint?
Yes, the generator of ASEP can be conjugated. If you go into the, it can be conjugated to make a self-adjoint operator on functions on point configurations in the lattice. Yeah. Okay. All right. So I'm going to diagonalize it. So I'll start with looking for eigenfunctions. Right? So the eigenfunctions can be found using the standard scheme of Bethe ansatz that goes back to Bethe in 1931. So it works as follows. I'll just briefly go through it. If I first look at the free part of my generator, which is what happens away from the walls, and that's just the sum of one-dimensional operators, so I can diagonalize one-dimensional operator, which is not a problem. Okay, so I diagonalize it, I get a bunch of eigenfunctions. I'll call them psi-z, where z is a complex parameter. These are just eigenfunctions of one particle generator. They are easy, and well, they're just where they are. They're just these. Okay, just a single variable function. Okay, now the second thing is that one takes linear combinations of products of such functions in the variables that I have with some coefficients, and those coefficients can be extracted essentially from the boundary condition via a recipe that's easy to come up with. You basically look for solutions in this form. You make them satisfy the boundary condition. That will produce some sort of a relation on these A's, and solving that relation produces something. Okay? So that's the scheme. I'm not going to do more than that. This S is the S matrix in Bethe ansatz. And that produces, in this particular situation, again, it's essential that I only have 2-point boundary conditions, and that produces eigenfunctions. Except for there are too many. Namely, for every k-tuple of z's complex numbers, I get an eigenfunction. This cannot be the analytic spectrum, right? I mean, the spectral theory must utilize something smaller than that. Anyway, so this is the explicit form of the eigenfunctions. These are the single variable or single particle eigenfunctions. And this is the S matrix part, and there is a symmetrization that's going on. So this is the eigenfunction with the property that when I take my generator, apply to it, I get a simple eigenvalue and that function back. Okay? As I said, my operator is not self-adjoint, so I will need the eigenfunctions of the transpose of that generator. They are not conjugated to the eigenfunctions that I have before, because it's not self-adjoint, but they're given by a similar formula, and you can see that there is a space reflection essentially embedded in here, and Q is being replaced by Q inverse, but that's really minor. There is this space reflection here is really playing the role, and then there is also this strange constant CQ in front. That's because my operator has the PT invariance. That means that I need to go to the equilibrium measure first. And so this factor here is responsible for going to the equilibrium measure. That my property works in the L2 space under a measure. But in any case, you can just check that these two expressions are the eigenfunctions of H and H transpose. Okay? So these are algebraic eigenfunctions. Now I want to use them in order to solve my system. I'll give a formal statement of what the Fourier transform is and the inverse transform is. Okay? So these will be mutually inverses on a certain spaces. These spaces are modest, and one can enlarge them, but for cleanness, I'll just keep them modest. One is the space of functions on n's that are weakly ordered. So these are my particle locations. This is the space in which I'm solving my evolution equation. And so these are, I'll take the functions that have compact support. I will call that space WK for the Weil chamber. Now the second space, this is my Fourier space. This will be the space of Laurent polynomials in variables z1 minus 1 up to zk minus 1. These are symmetric Laurent polynomials in these variables. The direct transform is going to be, as one should expect, the usual L2 pairing of a function with an eigenfunction. Okay? That's just what one should be looking for. Now, of course, the trick is to find the inverse transform. So this is the inverse transform. The inverse transform involves the integration, again, of whatever I'm transforming with the eigenfunction. But then there is a weight. Okay? So this weight here is essentially the inverse squared norm of this function. So I'm inverting the decomposition in eigenfunctions. And then there is an integration here that goes along big contours. So all w's are integrated over a big circle of some radius. Okay. So before actually making a statement, let me play a little with this formula, because this formula is not something you've probably seen before. So this is the top here. Yeah, question. Yeah. Yeah.
This is what replaces, so you don't have a so this is what you have instead of this I should understand this as when you plug in your operator, this is what comes instead of risk projector when you don't have a spectral theory. Am I right?
I don't know how to answer the question. I don't have the picture that you have in your head.
Okay.
So we can talk later. What I'm trying to do is I'm trying to do the analog of the Fourier transform, the way that Fourier diagonalizes Laplace, any constant coefficient differential operator. I'm trying to diagonalize my operator. So that's all I'm trying.
Are you trying to show you have a surplus of eigen
Yeah.
vectors?
Yes.
Are you trying to? Have you already explained to us how to?
So here, the inverse transform
Yeah.
utilizes w's that are my former z's that lie on big circles. So that's the restriction. Instead of utilizing w's being in the whole complex plane, I restricted them to certain one-dimensional contours. So this is my inverse Fourier transform that only utilizes part of my set of eigenfunctions. Okay? So this is
So you're just using the left ones, or?
the right ones are here,
Yes.
and the left ones are here.
Yes.
One of them participate in the direct transform, and those that participate in the inverse, those are the ones that participate in the spectral analysis, and those are the ones that live on the contour. So to reproduce my function back, having the pairing with eigenfunctions, I only need eigenfunctions that involve z's and w's living on these contours.
What's the delta Bose analog of the last formula?
What is the delta Bose gas analog of the last formula? Well, it's the same formula, so the integral will I'll get to that. It's hard to answer. So the answer in the repulsive delta Bose gas case is easy. It's a similar formula with the integral taken over the imaginary axis, with this thing replaced by its affine analog. But in the attractive case, I'll get to that. It's harder. There is no exact analog of that formula.
So if you plug in the first formula into the second formula, you get a formula for the, what I mean is that when you plug the first formula into the second formula,
Yeah.
the direct transform into the inverse transform should
Right.
get
So this is the statement. These two operators are mutual inverses.
But
If
if
you
I do it on the level of the form, if I just substitute it, so I get something like an integral over rank 1 operators, which are kind of projections, which are not orthogonal because we're not in the spectral case, and then you integrate. So it's
sorry, this is too long. I lost what you were trying to say. The statement that I will try to make is that if instead of this g, I plug in this expression here, then the output will be the original f that I started with. Okay, that's what I'm saying. Okay, and I can do it the other way around actually. If I start with some g, if I first do this, and then I pair it with the right function the way it's written, I will get back my function g from here. Okay, so in any order, I get the identity. This is an honest isomorphism between the spaces with an inverse. Okay. Now, I want to play a little bit with this formula. Okay. It's actually relevant. Okay, so this formula written here is the formula that was on the previous slide. It has integrals over the large contours, and these are the labels that participate in the eigenfunctions. Okay. Now, this intermediate formula, you see, doesn't involve any psi's. The reason that I can do that is that psi is a symmetrization of something. So if I have a symmetric expression, I can write the desymmetrized expression, and then going from here to here is a symmetrization argument. Okay. So this formula is arguably simpler. See, it's reminiscent of the formula for the q moments that I had before. It has similar structure, except for here I have an arbitrary function g, and there I had something else. Now, once I have that formula, I can go from large contours to nested contours. And then I can take these nested contours and I can shrink them back, and I can shrink them further to go just around 1. What will happen if I do that is that I will have to pick poles from here. As I pick poles, my formula will become more complicated, and the psi's that will enter will be psi's evaluated at certain pieces of geometric progressions. Because taking any pole here says that one z is q times the other z. So I will need to restrict here to certain geometric progressions. Okay? It's not trivial to go from here to here, but it works. So these are the so-called bound states in the Bethe situation. The reason I'm doing that is that if one tries to take limits of this q-Boson system to different parts, different formulas for the inverse transform will be useful. And it's kind of an intrigue to me, because the fact that I can't really choose which formula to use, it depends on what I need to do, it just means that I don't really know what the spectrum is. So my spectrum in the spectral theorem is whatever I integrate here over. That's my inverse Fourier transform. The labels give me the spectrum, the z's. My operator is not self-adjoint. I don't know where to put my spectrum so that the spectral measure is positive. Yeah.
You have the same formula for the self-adjoint case. You can write the operator, you can write a resolution of identities as a contour integral.
Yes.
And you also can choose the contour wherever you wish. So
yes.
you can argue that also in the self-adjoint case you don't know what the spectrum.
But there is the best choice in a way.
No.
Well, I think yes. That's.
In your case.
No, well, in the self-adjoint case, that's the contours on which the eigenfunctions have the self-adjointness property, that the left eigenfunction is the right eigenfunction conjugated. And that's also the contours on which the Plancherel measure, or the norm squared of the eigenfunctions, is positive. So that is the self-adjoint. So the xxz or the TASEP case has this feature, and the contours can be fixed there. Now, this situation, I don't know how to fix them. Now, moreover, the spectral structure here and here is different. See, here I have no bound states. My all w's are free. They go along a large circle. Now, here they go along a small circle, but I need to complement them by taking them bound, by taking some of them being q times the other. Okay. So this is kind of a weird situation for me. I don't know how to explain it. The formulas work. They're useful. I'll show how they're being used. But my spectral theorem doesn't really give me the spectrum. Okay. Fine. So this I already said what the theorem says. It says that the two transforms are really inverses to each other. Moreover, they are what they should be. So the dot products are preserved, where the dot products, what do I mean by dot product? So here this is just an L2 dot product. And here what I mean by dot product is a pairing that's given by this inverse transform. It's a weird pairing. It's not positive definite, because this thing here is not positive in any way. I cannot choose the contours to make it positive. But formally, I can write it down pretty nicely. The dot products are preserved. Now, and then the Bethe states are mutually orthogonal as they should be in both the space and the momenta space, right? So if I pair them in the complex variables, then I get the delta on the lattice, and if I pair them in the lattice variables, then I get essentially delta with the squared norm. Okay? So that squared norm is the Plancherel measure, and that is what goes into the inverse transform. Okay? All right. So this diagonalizes, although maybe not such a simple way, the Hamiltonian that I started with, the operator that I started with. Now I want to show how that can be used to actually solve my original system for some initial conditions. Okay, so what it says here is how this is being done. So this was my goal, to solve this evolution equation with this Hamiltonian, with some initial condition. So the initial condition is related to the initial condition of q-TASEP, and it could be random. That's just a reminder of what the operator was. And so the way one solves it is one takes the initial condition. So that's the standard way one solves evolution equation once you know how to diagonalize the spatial part. You represent it, so f naught is equal to jf f naught, right? So you just write it. This is a resolution of the identity. You just write it as a composition of the two. And then if you look at what J does, so J decomposes onto eigenfunctions. And so when I apply the evolution operator, it's linear in those eigenfunctions. So I just need to insert the e to the eigenvalue. And so then this here is the solution to this problem. I have rewritten this solution using the nested integral. So the nested integral is the simplest one out of the three forms that I had here. And so this is the solution for the initial condition psi naught. And so all I need to do now is to pair that f naught with the eigenfunctions initially. Now, I am trying to play down the difficulty. For a specific initial condition, evaluating that thing is something that may not be done explicitly. So for certain initial conditions, you can do that. And so step initial condition is an example of that. So for the step initial condition, f naught, so again, f naught is the expectation of q raised to the positions of the particles. If you have just one initial state, it's easy to evaluate what it is. And so it turns out that f naught is just a characteristic function of the positive half lattice in each variable. And so then g, so what is g? G is what sits here. Then it's easy to evaluate, and it's actually a simple object. In terms of the spectral analysis, this is what makes the step initial condition special. It's because you can really compute this thing. Now,
But you didn't compute it. You just looked at your old formula and guessed what went there.
that is correct. So this whole, and I'm happy you said that, actually, because this whole theory essentially appeared from that initial formula. Because that initial formula must have had a reason to exist. And initially, I thought that the spectral analysis problem is just hopeless because of the lack of self-adjointness. I just don't know what to do. But then sort of having that initial formula as a guidance, one can open this can and sort of get this out rolling. Okay. So there is a little trick that I wanted to mention is that, so computing that is difficult, but if your f naught is actually j times something, then putting f on top is easy because f just cancels j, and you read off what you had. So as usual in the Fourier analysis, this is a source of many non-trivial identities that that one can produce that way, just utilizing one as the inverse of the other for specific functions. And so this is one example.
You tried g's. Can you find out the other physical initial conditions?
Say it again. Can you find?
So now you start plugging in g's and see if you can find any other existing initial conditions.
Sure. I mean, the problem is that you need to ensure positivity in some way. And on the level of G, it's not obvious what positivity means. So here's an example. So this is an example of the so-called half-equilibrium initial condition. And so instead of just packing all the particles on the left densely, what I do, I spread them out by random amounts. And these random amounts are identically distributed and independent. And their distribution is the Q analog of the Poisson distribution. It's called q-geometric distribution. So this is just alpha to the k over k factorial, where factorial is in the Q sense. And the reason I call this half equilibrium is because if you take that configuration and spread it on the whole lattice, that's going to be the equilibrium measure for q-TASEP. Okay. Okay. So then so then I can do everything explicitly. In particular, that G that was here so simple, well, it's not so hard here as well. What happens is that instead of this thing having a singularity at 0, it has a singularity at a shifted location. Okay? That's all that happens. The initial condition sort of changes quite a bit, but on the level of Fourier analysis, the only thing that happens is that instead of Zj here, you have Zj minus alpha over Q. Okay? So in principle, one can actually propagate that. So instead of having just one pole here, I can put any number of them, let's say finitely many. That will give a valid initial condition for q-TASEP. That's going to be a random initial condition, and for that we can do the analysis. And we actually, for these initial conditions, we actually put the whole program through. So we had the limit to kpz, and we got the formulas for kpz with corresponding initial conditions. Okay. So this is the type of the good initial condition. Okay. So that I already mentioned. The similar story takes place for ASEP and XXZ, except for there the operator is self-adjoint, so there is no schizophrenia as to which contours to choose. There is a prescribed set. And actually, that was the subject of old papers. I was very surprised to find these old papers of Babbitt and Thomas and then Babbitt and Gutkin, where they essentially developed that, or something similar to that. The problem is that these papers don't really have proofs, and the proofs were in preprints, and it seems that the preprints have been lost. At least that's what the email correspondence with Babbitt and Thomas suggests, and Gutkin I was not able to find. However, I found his email, but he never replied. However, they have formulas that are fairly similar, and essentially what we do, we have an approach there that is not the one that they had, certainly, and probably simpler, so I don't really care about the proofs being lost. What I care about is that it doesn't seem that people in the subject picked up on what they were doing, and there are very few references to their work. It seems that it's just gone missing somehow. Okay, so the theorem that I showed, this Plancherel decomposition theorem, it has degenerations, which I'm about to explain a little more. There are two different degenerations in the discrete space, and then both of them go down to the delta Bose gas. So this is really deformation of the delta Bose gas picture. In the delta Bose gas, Oxford here, who sort of developed the completeness of the Bethe ansatz, was a student of Babbitt, but then he dropped off of math, dropped out of math. That's what Babbitt said anyway. And so Heckman and Obdam actually had the most complete understanding of the Plancherel theory in the delta Bose gas situation. This is how the degeneration works. I'll just say it in terms of the eigenfunction. So this is my eigenfunction, right? So this is the Bethe ansatz eigenfunction. And then what I can do, see, this is one limit. This one is being removed. Okay? That just corresponds that my z's are very large. And so these eigenfunctions are actually known. They're called Hall-Littlewood polynomials in representation theory, and then they came up in 60s. And their orthogonality and Plancherel transform is well known. Again, this is a self-adjoint situation, so there are no surprises there. Now, this here is a different degeneration. Here, my z's become close to 1, and you see that the q thing here gets replaced by the affine shift, by 1, and then this is getting replaced by z to a power. This corresponds to the semi-discrete Brownian polymer or semi-discrete stochastic heat equation. And it's also a non-self-adjoint case, and as far as I know, the spectral results are new there as well. And then both of them, they go down to the situation where the shift is here again is affine, it's just -1, and then the power just goes to the exponential. And so these are the eigenfunctions for the delta Bose gas. Okay. So I have a little bit of time, and I will allow myself to say things, to try to explain a connection. I don't have to say new things here, but I want to explain why. So I mentioned here that Heckman and Obdam have the best treatment of the delta Bose gas. Okay? So Heckman and Obdam are not mathematical physicists. They are representation theorists. And why they would have something to say about quantum delta Bose gas is not obvious. So what I'll try to do is I'll try to explain at least the idea of why this is related to representation theoretic objects. And right, okay. So what I wanted to say is that where do Plancherel theorems come from? Okay, so Plancherel theorems of Fourier type transforms are very non-trivial objects, especially in many-dimensional situations. Where do they appear naturally? So what is Fourier transform? So Fourier transform is a tool to diagonalize constant coefficient differential operators on the real axis. Okay? So the same idea of trying to diagonalize differential operators on harder spaces actually underlies many of the multidimensional Fourier transforms. Okay, I'll skip this example. This is a purely representation theoretic example. I can tell you later what it means. So this is the simplest example for the diagonalization of differential operators on the homogeneous space. Okay. What if I try to diagonalize Laplace on the sphere? Okay. So the sphere is a homogeneous space. This is SO3 factored by SO2, where SO2 rotates around a single axis. And so if you just take all functions on the sphere and diagonalize the standard Laplace transform on the sphere, that the spectral decomposition will actually have multiplicities. There will be spaces with same multiplicities, with same eigenvalue. Now, what you might want to do in a situation like that is to get rid of multiplicities and just look at the decomposition itself. So that procedure of getting rid of multiplicities in many good situations, in many homogeneous spaces, amounts to restricting your action to functions that are invariant with respect to this SO2. So instead of just taking the quotient with respect to the k action on the right, you also take the quotient with respect to the action on the left. So on the sphere, it means that you want to look at the functions that will be invariant with respect to rotations in that direction. So these are just the functions that depend on this theta. Okay. So it turns out that if you restrict yourself to that space, then the spectral analysis is simple in the sense that the eigenvalues are simple. This is the operator, and the eigenfunctions are the Legendre polynomials. And so the Plancherel theorem is the decomposition of L2 with respect to the Lebesgue measure on -1, 1, or sine theta, d theta measure on 0 pi, into the Legendre polynomials, with the squared norm being the squared norm of these polynomials. So this is actually a general principle. What happens is that if one looks at the symmetric spaces and then decomposes that space under the action of the group into reducibles, then you'll have blocks. Those are the blocks on which something like Laplace will be scalar. So these are blocks of high multiplicities of Laplace. And then if you want to know how these blocks are distributed, then you've got to take in each block a single vector, which is called a spherical vector. This is taking the invariant vector here. And then on those spherical vectors, you have an honest Fourier analysis. You get the Plancherel theorem. So the Plancherel theorem sort of rides on top this general decomposition of the L2 on the symmetric space onto irreducible representations with respect to the group action. Okay? That's sort of the origin of many things. And so for the real semi-simple Lie group, that's the source of a beautiful theory of Gelfand, Naimark, and Harishchandra. So here my spectrum is quantized. That's because my symmetric space is compact. But if it's not compact, then you get integrals instead of sums, and that's where the continuous spectrum comes into play. Okay? So that was actually the reason why Heckman Obdam were doing that, except for they were doing that not with a group, because there is no group that corresponds to the quantum to the delta Bose gas. They were doing it with the Heck algebra. So the Heck algebra is something that people extract from the group, and then there are some structural constants there that then people can make arbitrary. This will still be a well-defined algebra, but there will be no group associated to it. So the quantum delta Bose gas has a coupling constant, which is, well, okay, which is the coefficient in front of the potential, in front of the sum of delta xi minus xj. So for some specific values of that coupling constant, there is a direct relation to representations of groups. But then if you want to make that constant arbitrary, there is no group anymore. Groups don't have that freedom. You can't put a constant into a simple Lie group or something like that. So you've got to extract something from that group where you can make the coupling constant arbitrary. And so Heck algebras, they realize that idea. So in that situation, this Heck algebra that they deal with is generated by the simple reflections which permute two coordinates and differentiations in x's and with certain explicit relations. And what they do, they look at the functions in n variables, and they decompose that space with respect to this action. And then when they restrict that onto the symmetric functions, which is the spherical vectors, they recover they prove essentially the Plancherel theorem for the delta Bose gas. So the generator for the delta Bose gas plays essentially the same role as the Laplacian plays on the sphere, except for the symmetric space needs to be different. And then again, I want to say that this philosophy of symmetric spaces is extremely powerful. And then the whole business of trace formulas and Selberg trace formulas, for example, came from doing a similar thing when the subgroup K is a discrete subgroup. And the theory of automorphic forms essentially is doing what I'm saying here for different choice of G and K. So that really is the underlying origin for these formulas. So then it's natural to ask whether there is a representation theoretic background for the Plancherel formula that I mentioned. And the answer is I don't know. Okay, it's very recent, and I'm very sure that there is, but we haven't developed it. For the two degenerations, so I mentioned here that there are two degenerations, right, for these two. So this I said, this is the graded Heck algebra. That's what Heckman Obdam realized. Now for these two, the answer is actually known. So for this one, the representation theory is related to p-adic fields. And so that's what was done. That was the major work of MacDonald way before he introduced MacDonald polynomials, and that led to the Plancherel statement related to these whole Littlewood polynomials. And then for the other degeneration, there is a recent paper by Takeyama who realized that there is a slightly more general affine Heck algebra that acts there, but he didn't do any harmonic analysis, so that's still so harmonic analysis is this decomposition into blocks, and that's still one needs to look at it. All right, so I wanted to make this link so that it would look less mysterious as to where these formulas really originate from. Why there are these sort of pretty mutually inverse operators acting on several variables that happen. Okay, so there is a connection with MacDonald polynomials. Let me just spend 1 minute there, and I'll be done. You might remember from the last time, sorry to rely on that there were these first order difference operators that were diagonalized by MacDonald polynomials. Okay? Now, how are they related to what I spoke about now? Well, so they have an interesting property that I wrote here, that if you take the kth power of this operator and you commute it with multiplication by the sum, then this can be written as a linear combination of operators. So n here is the number of variables. This is n minus 1 variables, 1 through xn minus 1. And what's written here is essentially the generator for the q-Boson particle system. See, you had k particles at location n. One of them jumped to the left to location n minus 1, and this is the multiplicity that came out. This is 1 minus q to the k intensity of the particle jumping left. Okay? So what I'm saying here is that somehow these McDonald operators know about the q-Boson system. That can be utilized to produce many solutions for the q-Boson system in a different way. So now I produced my solutions by diagonalizing the Hamiltonian. Here is a different way to produce many solutions, actually all of them. Very different way. I take my operators in different number of variables. I apply them to an arbitrary function. And then I put exponential, then I take away with it. So I claim that whenever I write an expression like that, this is the solution for the evolution equation of the q-Boson system. Okay? And the original one that I started with, the step initial condition, corresponds to this f being simply 1. The half step initial condition corresponds to this f being something like 1 over x minus alpha or something like that, the product over all variables. Okay? So there are two ways to produce solutions of the system. How they talk to each other, we essentially don't know. So the information is being transported through a very nonlinear map from this f here into, let's say, the initial condition of the q system. And this is an isomorphism. But it would be nice to know more about that isomorphism. So this connection between the McDonald theory and the Plancherel theory for the q-Boson system hasn't really been developed, and it's actually the largest mystery to me in the subject as to why that connection exists and how it works. So I'll just summarize what happened. So we wanted to diagonalize the q-Boson system, and the reason for that is that we essentially wanted to mimic what physicists were doing with the delta Bose gas to solve KPZ for a variety of purposes. You know, in their replica trick, they can do multi-point computations that are actually even beyond what universality predictions we have. But to do that, Dotsenko in particular utilizes the fact that he can solve the delta Bose gas solve with replica for any initial condition. So to get any sort of access to those answers and to have some firm footing, we needed the rigorous version of that. And so that's what the original motivation comes from for that theory. Now what happened is that, unexpectedly to me at least at first, is that the Plancherel theory or the Bethe ansatz theory is nice and complete, and everything is explicit, and it's an isomorphism statement. It's sort of clean. And hopefully we can now take that and go back to what Dotsenko made a path for and see if we can actually nail down the exact statements there. That hasn't been done. This work is recent. We are not there yet. There is a similar Plancherel theory for ASEP, and actually by now we understand that there is a more general Plancherel theory that degenerates to q-Boson and to ASEP in two different ways. And we are on the way to writing that up. As I mentioned, the connection to McDonald's is there. It was the original push that made us try, but why it's there, I can't give deep reasons or any reasonable reasons actually. And then finally, as I already said, what we've done so far is algebra, turning it into the KPZ universality class information further than what we've done for the half equilibrium initial condition or its variance or the step initial condition. That will require more analytic work, and that's not been done so far. So that's all I wanted to say. Thank you very much for listening.